All right, so next we're going to talk about significant figures. And you've probably discussed this if you've had science classes before, but we're going to review it again. Okay? Scientific measurements are reported so that every digit is certain except the last digit, which is estimated. So, in other words, we know if we report a number as 5.213, that means that we know that the 5.21 are correct, but we're not sure if the 3 is correct. This could be 3, this could be 2, this could be 1, this could be 4, this could be 5. We're not really sure that last digit. Okay. And that's because when we measure things, there's never a certainty in that last digit. Like if you have a scale and you put a lump of coal on the scale and your scale reads 4.537 grams. Okay. That means that you know this lump of coal is 4 grams. It's not 3 grams or 2 grams or 5 grams, it's 4. And you know it's 4.5. And you know it's 4.53. But you might have noticed this scale might keep jumping around from 4.535 to 4.536 to 4.537 to 4.538 to 4.539 due to fluctuations in the, let's say, the air current in the room. So this last digit is where we call the uncertainty. And so we want to report our numbers to the correct number of significant figures. So this lump of coal weighs 4.537 grams, but we know that the 7 is uncertain. If we write down 4.5372 grams, then this is wrong because we don't know anything about that digit. Okay, so so if we add two masses together, okay, so let's say our scale wasn't large enough to weigh something greater than 10 grams. Okay, this is a good example. Let's say that we have a scale that is very precise, and our scale only measures up to 10 grams. But we have, let's say, let me think a minute, something I can tear apart. Let's say we have a lump of coal. And let's say we know this coal weighs about 12 grams, but we can't measure it on our 10-gram scale. Okay. Scale only goes to 10 grams. So what am I going to do? I'm going to cut my lump of coal in half, and I'm going to weigh these halves one at a time. And I'm going to add half A plus half B. I'm going to add those two masses together. Okay. So I take the first half and I put it on my scale. Okay, and I get 6.319 grams. Okay, and so I'm going to record that 6.319. And then I take my second half and put it on the scale. Okay, I put the second half on the scale, and let's say I get 4.810 grams. Okay. So then I've got 4.810, okay? And just so I don't make a mistake, I'm going to go ahead and add that on the calculator, even though I can do that in my head. So 6.319 plus 4.810 equals, and that gives me 11.129. Now I couldn't have weighed those both at the same time. I had to add them together. So the question is this 11.129 do I have the correct number of significant figures here? Okay. Well, it turns out that I do, because when I'm adding and subtracting, I'm going to be looking at the number of decimal places, and I'm going to keep the number of decimal places that I had. Okay. But if I'm multiplying and dividing, I'm going to be limited by my lowest number of significant figures. So we're going to talk about that. But the point is, you can't have, if I had written this answer as 11.1293, let's say, then this 3 is just plain wrong. My uncertainty lies in the last digit, and I have to only report the correct number of significant figures, which indicates that the uncertainty lies in the last digit. Okay, so here are the rules for significant figures. All non-zero digits are significant. So for a number like 28.03, let me change colors. All right, 28.03, then every number is significant. The 2, the 8, the 0, and the 3. Well, we'll get to that in a minute. But all of the non-zeros are significant, 2, 8, and 3. Okay, so if you have a number like 0.0540, the 5 and the 4 are definitely significant because they're non-zeros. Now, we haven't said that any of these others aren't yet, just that the 5 and the 4 are. Interior zeros between two non-zero numbers are also significant. So what we're saying here is interior zeros like this are significant. Okay, so for example, in 408, we know that the non-zero numbers 4 and 8 are significant. The 0 is also significant because it's between those two non-zero numbers. 7.0301, the 7, the 3, and the 1 are significant because they're non-zero digits. And the 0 and the 0 are also significant because they're between two non-zero digits. Okay, so all of those are significant. Right? So moving on, leading zeros to the left of the first non-zero digit are not significant. Okay, so if you have like a decimal number, leading zeros on the left are often there for a placeholder. So for example, if I converted, let's do this. Let's say I converted 10 milliliters to liters. How do I do that? I divide by 1,000, or I move my decimal point 3 places to the left. Okay, so I move my decimal point 3 places to the left, right? So I have to put these zeros in just as placeholders, but my original number was just 10 milliliters, right? So these numbers were added as placeholders, and that's why they're not significant. So I'm just explaining why these are placeholders and they're not significant. So like for 0.0032, these are not significant. They have to be there. They're placeholders. For 0.00006, these are placeholders. They have to be there. So only the 6 is significant. Moving on, trailing zeros at the end of a number are significant if they follow a decimal point. Okay, I keep touching the wrong thing again. Okay, if they follow a decimal point. Okay, so in this case, 445.000, let's go back to our scale. What if I said I could weigh up to 10 grams, right? Let's say I put a lump of coal on here, and that lump of coal weighed 10.000 grams. Okay, so I know that lump of coal to 3 significant figures. I mean 3 decimal places. My uncertainty lies here. Okay? So I'm going to report that number to the last point of uncertainty because my scale is going to give me 3 decimal places. So it's going to be 10.000. My uncertainty lies here. That means all of those zeros are significant, actually. So trailing zeros after a decimal point are significant, okay? So like here and here, even if there's numbers before them, those are also significant. Trailing zeros before a decimal point and after a non-zero number are significant. So like for 140.00, if you can see that decimal point, that means we know the uncertainty lies there. Okay, if they're between the two non-zero digits, of course, they're significant anyway. Trailing zeros before an implied decimal point are ambiguous and should be converted to something more certain with scientific notation. So we'll often use scientific notation to clarify ambiguity. So let's look at how that works. Okay, so here we have a number 1200. So I don't know whether this number means 1200. Some books will actually report a decimal point there to mean that I have 4 significant figures. So what I'm saying here is how many significant figures do I have? How many of these numbers are significant? So for 1200, I don't know whether it is 4, okay, where meaning all of them are significant. Or I don't know if my measuring device could only measure to the tens place, and maybe this number is where my uncertainty lies. Or maybe my measuring device can only measure to the hundreds place. Maybe I'm measuring the stuff by the ton, okay? Maybe I'm pulling my car up onto one of those scales like you go by at the dump, and it doesn't have much uncertainty at all. It can't measure grams, right? So maybe my uncertainty is there. So we don't know. This is ambiguous if we don't have a decimal point. It's ambiguous. You don't know whether your uncertainty is here or here or here. Okay, it could be either of those 3 places. So we have to use scientific notation to make that unambiguous. And we report scientific notation by, let's do that. Let's report scientific notation, go over that real quick. All right, so to convert a number to scientific notation, let's go back to our 1200. Let me change that to 1206, just to, yeah, 1206. Okay, just to make it a little less ambiguous. Okay, so I'm going to convert that to scientific notation. So to do that, I know my decimal point would be here right after the ones place. I move the decimal point until it's right behind the first number. And so to convert that to scientific notation, my new number would be 1.206. I move the decimal place 3 places to the left, 1, 2, 3. So that's times 10 to the third. Okay, times 10 to the third. So to get my number back, I would have to multiply by 1,000. If I multiply that by 1,000, I would get 1206. Okay, so that's 1.206 times 1,000 basically. All right, so let's convert 1200 to scientific notation. So I can do that with two. So I've got 4 significant figures here, but for 1200, we don't know whether it's 4 or 3 or 2 significant figures, but we can clear that up with scientific notation. So if we have 2 significant figures, we're going to move the number behind the first um, digit, and we're going to say 1.2 times 10 to the third, because to get our 1200 back, we have to multiply 1.2 times 1,000. If we have 3 significant figures, then I'm going to do the same thing. I'm going to put my decimal point behind my first number, but I'm going to carry 1 0 along with it. So that'll give me 1.20 times 10 to the third. It's still multiplying times 1,000 to get my 1200 back. If I multiply times 1,000, I get 1200. Okay. Now, if I want 4 significant figures, then I'm going to say 1.200 times 10 to the third, because if I multiply by 10 to the third, which is 1,000, I get my 1200 back. So all of these numbers, 1.2 times 10 to the third, 1.20 times 10 to the third, 1.200 times 10 to the third, they're all equal 1200. They're all the same number, but they all have different numbers of significant figures, and the uncertainty is in different decimal places. The uncertainty is here for this one, here for this one, and here for this one, and therefore we have to clarify the uncertainty by adding the significant figures in. All right, and so we will do some more problems with that. Let me move on a little bit. We got a few more minutes. So I'm going to go ahead and finish up significant figures today. All right. So before we do that, let's talk about exact numbers. Exact numbers have an unlimited number of significant figures. So, for example, discrete objects like marbles are exact. We don't count half of a marble, right? I mean, you shouldn't unless they're broken, right? So if I had 5 marbles, I would have exactly 5 marbles. I wouldn't have 5.5 marbles. I wouldn't have 4.9 marbles. I would have 5 marbles. Discrete objects are exact. If I had 5 pennies, I would have exactly 5 pennies. Okay. So they have an unlimited number of significant figures. So these 5 pennies would be 5.00000000, as many zeros as I need to put in to have my significant figures not limited by that. Okay, so I can use as many zeros as I need, as many significant figures as I need. Integral numbers that are part of an equation are not limited by significant figures. So in other words, if I need to multiply my equation by 4 or something like that, then I don't limit significant figures by that. And also defined quantities are not limited by significant figures. Now, most conversion factors are not limited by significant figures. So let's talk about significant figures and calculations. So how do we calculate significant figures? So multiplication and division, the significant figures are limited by the number with the fewest significant figures. So here we have 4, here we have 5, here we have 2. If we multiply those 3 numbers together, we're limited by the one with the smallest number of significant figures, so we have to end up with 2. Here we have 5, here we have 3, and we're dividing, so we can only have 3 significant figures in our answer. So if our calculator gives us this, we have to round to 3. Okay, so we'll talk about rounding in a minute. If the calculator gives us this, for the top number, we have to round to 2. So we can only have the significant figures that is limited by the smallest number of significant figures for multiplication and division. For addition and subtraction, we're limited by the least number of decimal places. So if we have 1 decimal place for the lowest number, then we're limited by that. And we have to round to 1 decimal place in our answer. If we have 2 decimal places, then we're limited by that, and we have to round to 2 decimal places in our answer. So for addition and subtraction, you can actually gain or lose significant figures sometimes. And we'll talk about that. We'll see some examples of that.